All right, so thanks for coming. Well, the ultimate goal of this lecture is actually to give a brief overview of how, jets is something that's been used in particle physics in something like 40 years. It's still used now, and probably one of the biggest use of jets now is something called jet substructure. So my end game is typically to give you an overview of the broad range of application that jet substructure has had in collider physics, in particle physics in general. So the question is how to get there. How to get there, I probably have to start with some basic playground and more basic stuff, including before discussing jet substructure, I need to discuss jets, and to discuss jets, I need to discuss a little bit of collider physics. So the big question is, how much collider physics do I need to discuss? And that probably depends on what you already know about collider physics. So my goal was to organize these lectures as having a first lecture trying to give you what a jet is. So just to make sure, just try to gauge who I'm talking to. Who here has already heard about what a jet is? Who here thinks, at least, yeah. Heard the word jet. Knowing what it is probably another question, but okay, we'll get there. Who here has already heard about jet substructure? Okay, good. Who here knows what jet substructure is? Okay, 2, 3, okay. Let's see what we can do in this context. So the first thing I like to do is, what I'm going to talk about, there is a plan. You can read either on the web page or on the poster. That plan is at best a tentative preliminary version, okay? So if there's anything I'm going to speak of, essentially all the topics I'm going to cover here can be themselves extended into a full set of lectures. So if there's anything I'm going to speak of that I don't know, if there's something that's missing, just you want absolutely to hear, and that's missing, just let me know. If there's something that seems completely trivial to all of you, just let me know and I'll move forwards. That would actually give some time to discuss something different. So don't hesitate to interrupt, ask questions, or even ask me to talk completely about something not covered, that I was not initially planning to cover. So the goal of this first lecture is just to introduce the concept of jets and essentially laying the ground to making a firm ground to build from that to the next level, which would be jet substructure over the next set of lectures. The ultimate goal is actually, as I said, to cover the fact that, try and illustrate the fact that this tool is around since 40 years. It's something that has a broad range of applications. I won't obviously be able to cover all the applications, so I'll have to make choices. And again, that's one of the cases where if there's some specific topic that you'd like to discuss and I'm not planning to cover, just let me know, preferably before the Thursday before my last lecture, okay? So this first lecture is mostly about jets. And to do this, I'm first going to start with a bit of generic collider physics. In particular, some stuff that I'm going to need for the lectures for the next weeks. And there's essentially two. So the goal of collider. Let me start with just trying to briefly remind you of the goal of collider physics. So I'm going to talk about two extreme examples. They're not quite as extreme as you can probably think of, but one is to discuss the case of E plus E minus collisions, and I contrast this with the case of PP collisions. So think LEP on this case, and think LHC on this case here. So the idea in both cases is the global idea is the same. So you want to collide particles, look at what happens in the final state, and based on that final state, you want to understand what interaction happened at the core of the collision. All right. So that's the same in both cases. What you will do with, so this is a lecture about jets, so if that has not been clear, I guess it's clear for everyone, jets are part of Qcd, so I'm going to be mostly focused on Qcd in this case, even though one of the applications is to use QCD or use jets in order to probe beyond the standard model interactions. But still, I'm going to be primarily focusing on QCD interactions here. And I think in terms of what you want to do with QCD, these two cases are quite different. So in this case, I'm just going to collide an electron-positron collision. This interacts, say, via, the basic interaction is via a Z or a photon. I'm going to concentrate on the photon case to avoid all sorts of mass effects and V minus A interactions. So typically, this will end up in some final state, either E plus E minus, mu plus mu minus, or QQ bar in this case, or neutrinos if you want. But I'm going to focus on QCD final state for the most of these lectures, okay? So it's typically E plus E minus going to QQ bar that I'm going to be interested in, and that's what I'm going to discuss for the first hour. In the case of proton-proton collisions, this situation is a bit more complicated, but I'll get there in a minute. So the idea is, out of this interaction comes some particles, and based on these particles, you want to understand what happened here. So this would be E plus E minus. So the typical way a collision occurs is, and again, I'm just saying this to lay the ground so we start on the common point. You start with an E plus E minus collision that produces QQ bar. These Q and Q bar are going to radiate further quarks and gluons, all right? And they're going to, I'm always going to say, to work in a limit where the center of mass of the collision is large, and by large here I mean much larger typically than lambda QCD, or if you wish the mass of the proton, some soft hadronization scale, some soft hadronic scale. So it's a high energy collision, and typically if you have a high energy, there's a huge phase space for radiation between this high energy and this softer scale, and so you're going to radiate partons that are going to populate that phase space. So if you radiate partons that are going to populate that phase space, at the end of the day, you get a bunch of partons, and you get a typical energy scale, which is around 1 to a few GeV. And at the moment where this scale is a few GeV, these partons, quarks, and gluons are going to, say, hadronize and give you a bunch of, say, pions, protons, kaons, whatever hadrons you're going to have and observe in the final state, okay? The situation of proton-proton collision is, give or take, the same. The main difference is that since you collide, E plus and E minus do not carry any QCD color charge, but if you carry protons, protons themselves are hadrons. So protons themselves interact via QCD, and so the typical way you would describe an interaction like this, at least at high energy, is that outside of one of the protons, you're going to take some parton, so a quark or a gluon from the other colliding particle, and these quark and gluon then do exactly the same. They do give you a bunch of final state particles, all right? There's essentially two differences between here and there. One is that since the particle, again, this has a huge phase space to go from square root S to typically lambda QCD before the moment where your partons, quarks, and gluons hadronize into pions, kaons, and whatever mesons and baryons you want to observe in the final state. The main difference here is that, there are two main differences. The first one is that you're actually, in this case, it's literally E plus E minus that collide. So your collision typically happens in the center. The center of mass of the collision is typically the same as the center of mass of the lab frame, the detector. In this case, since you're colliding with particles, quarks, and gluons, these quarks and gluons will only carry a fraction of the longitudinal momentum of the proton, and they're not guaranteed, or actually most of the cases, they don't carry the same longitudinal momentum fraction. So this means that the real center of mass of your interaction is actually longitudinally boosted compared to the center of mass of the detector. So that's the first difference, and I'll give you one direct consequence in a second. The second consequence, the second difference is that these protons themselves carry QCD color. So these, and once you take, I don't know, take a high energy gluon outside of the proton, what's left is an object which is itself not color neutral. It carries still some QCD interaction. So this means that after this, there will be all sorts of interactions, typically soft interactions, because this is soft of the order of the soft proton mass, and the rest of the event. So there will be all sorts of soft interactions between whatever you observe in the, say, the typical hard partonic interactions in your event, and the rest, and the incoming beams. There's also going to be possible some radiations from the incoming quarks and gluons themselves can radiate quarks and gluons, which is not the case, obviously, if you do electrons. So I think the bottom line here, so this effect of soft interactions that happens around a scale like this is something called the underlying event. And so the main differences between, the main conceptual differences between the two systems is that this is a much more simple type of collisions with only QCD in the final state and no strange interaction, soft, non-perturbative interaction between initial and final state, while this is much more busy, a lot more QCD already partonic interactions, plus extra interactions between initial and final state, soft interactions. And the second one is that the kinematics is expected to be slightly different because this is a center of mass collision, while in this case the center of mass is boosted. So just to make sure we're, just to set the notations once and for all, in this case, if I have a 4 momentum somewhere in the final state, I'm typically going to discuss this 4 momentum as some 3 vector. Again, think about this as using spherical coordinates. I'm going to use a 3 vector and energy. And this 3 vector typically is going to have, if this is, there's always a preferred direction in this case, right? There's always the z-axis in this case. So you can use this as being, for most of the case, I'm going to work assuming things are massless. So in this case, it means that the modulus of k is equal to E. And you can describe this using either a 3 vectors, a unit direction on a sphere, or using some angular around some angle to the z-axis, so some cosine theta, let's say, and some azimuthal angle. While if you do this in proton-proton collisions, what you're typically going to do is you need to take a system of coordinates that properly implements and encodes the fact that your center of mass can be boosted. And so what you're going to typically do is represent some, so since your system can be boosted, what you're going to do is instead of using spherical coordinates, you're going to use some form of cylindrical coordinates with a cylinder along the z-axis. And for this, what you're going to typically do is, I'm actually using a slightly non-conventional notation where I put the energy at the end instead of the beginning, and this will probably be obvious now. I'm going to represent this as some, so you need 2 energy coordinates and 2 geometric coordinates. So typically what you do in this case is separate coordinates which are transverse, so transverse to the beam, and coordinates which are longitudinal to the beam. And in this case, what happens is that there's some kT, which is transverse momentum, times some angle, and some other, let me call this mt for the moment, times some hyperbolic sine of y, and mt times hyperbolic cosine of y. So this is typically the x momentum, kx. This is ky, this is kz, and this is the energy of k. So this is, say, just a representation of 4 vectors. If your 4 vectors are massless, so the mass of this object is e squared minus this momentum, so the mass squared of this object is mt squared minus kt squared. So if the object is massless, mt is equal to kt. So far so good? So again, this is just to lay the ground for later work. There will be, so most of what I'm going to say in actually quite a few of the lectures, you can just apply it to either this or this, blindly, just blindly replacing coordinates. So you would just replace, in this case, you would just replace the angle between, what you would typically use is some energies and the angle between different particles. So if you have two particles, you will use EI, EJ, and the angles between two particles. In this case, if you have two particles, what you're going to use is KTI, KTJ, and instead of the angles, you're going to define the angles again on that cylinder, which is something I'm going to call delta Rij, which is square root of delta Yij squared plus delta phi Ij squared. Again, delta phi here is to take into account periodicity. Am I missing anything here? So again, this choice is mostly motivated by longitudinal momentum invariance, well, longitudinal boost of the center of mass in this context. And so the set of coordinates you're going to use is slightly different. There's another difference in terms when it will come to describing the physics. So think about now the case where the final state is purely QCD, all right? Or the final state is, well, what you want to do with QCD in the final state. I think in this case, since the situation is extremely simple, there's no underlying event, hadronization, there's no activity, all the hadronic activities in the final state, this is typically a use case where you want to do precision measurements. You have very little extra soft unknown activity besides hadronization, so this is typically the case where you want to do precision. This is even the case now. Think about a stereotypical measurement in QCD, which would be measuring the strong coupling constant. This is still how you would do it mostly today, at least in terms of collider physics. Now, in this context, since the situation is much more complicated, making precision measurements is much more complicated as well. Now, what you typically do is imagine you want to do some, that's typically the context where you want to do rather searches for new physics. Because in this case, if you quote unquote just want to find some new phenomenon, you don't necessarily care about ultimate precision. You rather care about seeing deviations from something you know, and this is a context where you would do that rather in a way more easily than in this context. All right? So just to keep things clear, usually I'm first going to discuss jets in E plus E minus, keeping in mind that this is something you want to use rather for precision physics. Then I'm going to discuss jets, how to generalize this in the context of PP collisions. All right? So discussing jets in E plus E minus collisions is essentially covering history from the 1970s to before 2000. And discussing jets in PP, essentially, I'm going to swipe under the rug every history before, before 2000 maybe. So, the first question is, imagine you do an E plus E minus collision, and you look at all the particles in the final state. You essentially want to use QCD or whatever. You want to study the final state, and the first question you want to ask is, what's the topology of the final state? Can I learn anything about, if I produce QCD in the final state, what are the generic properties of that final state? And the very first question you can ask is my final state looking more like a uniform? I cannot really draw in 3D easily, so I'm just going to draw everything as a plane. Is my final state looking like this? Or is my final state looking like this? Namely, do I have particles which are distributed uniformly? If I look at one collision, do I have particles which are distributed uniformly across the whole sphere, or do they tend to align on a few directions? I guess you all know the answer to that question, right? But again, to put things in context, that was, say at the time of LEP or even previous colliders, that was one of the motivations to study the final state. Actually, to give you a more, probably more appealing example, last June, I think, was the 40th anniversary of the discovery of the gluon, and the discovery of the gluon just happened in looking at in events like this. All right. So to do this, you don't need jets. What you would typically use in this context is something called jet shapes, or event shapes in this case. The name speaks for itself, right? It's just trying to characterize the shape of the final state of the event. And so you would define, this is typically a function, so what you have at your disposal is a list of 4 vectors. I'm going to neglect all detector technicalities, whether you are able to extract these or not, but you have a list of 4 vectors in the final state, and based on that list of 4 vectors, you want to characterize the shape of your final state, whether it's more like this or more like this. Or I think I'm going to start with something even simpler, just one direction. All right. So, do you have any candidate for this? Or do you know any candidate for this? No one? How would you define one observable? I want essentially out of one event associate one number. Is there anyone who has any idea of how I can do that?
For one event or one single particle?
Well, what you want to do is measure something that for one event, which is one set of final state particles, for that matters, I want to associate just one number. And then you can just measure the distribution of that. Take only the finals, the hadrons, for example. But again, the difference between that and reality is just detector. I'm going to allow myself to stay theorist here and not dig into detector effects or experimental effects more generally. So you have a set of particles in the final state. Think about these as either hadrons or even partons if you want, or assume a perfect calorimeter and tracker in your detector, and assume what can you do with this in terms of. There's actually a bunch of known candidates. None is that easy. Really the typical example is something called thrust, and it's defined this way. T is the max. You're going to pick a direction. So imagine your sphere. I'm going to take a direction u of modulus 1. So take a direction on the sphere, and what I'm going to do is project all the particles in the final state onto u and normalize it by the sum of energy, essentially, for massless particles. Does that do the job? Well, this is not such an easy construct because you have to take a maximum over all possible directions. It's actually not, technically speaking, it's not an easy operation.
What about taking the minimum, minimizing this delta R, distance, take the square, the sum of all particles?
So I'm going in plus and minus. So you want to do, well, fine. All right. That actually brings a question I forgot to ask at the beginning. Who here is not familiar with the concept of infrared and collinear safety? Okay, good. I was actually planning to cover this at some point. The question is when. Maybe the answer is no. So at the end of the day, you want, well, I'm jumping a little bit ahead, and that's why I was actually not sure exactly when to speak about this. If you do QCD has a tendency to radiate quarks and gluons. If you start with a high energy parton, that high energy parton is going to radiate particles. I'm going to show explicit examples later. But typically, if you have a parton, that parton, if you radiate gluons, that's say the probability of emission, the probability of emitting gluons from either a quark or a gluon typically diverges into limits. It diverges when the angle here, theta, goes to 0. So if theta goes to 0, the emission goes like d theta over theta, so it's a logarithmic divergence. And if the energy of the emitted particle goes to 0, you again get a dek, a logarithmic divergence. Can you tell me in one sentence why do you have these divergences? Where do they come from? I guess here I'm asking the questions to all the amplitude people in the audience. Now, think about this as coming from somewhere. I don't know. Something like this. What happens if either this angle goes to 0? Remember, I'm working with massless particles. Either this angle goes to 0 or this energy goes to 0. What happens to this, say, amplitude, graph, whatever? If you write down the amplitude for this, you're going to have a propagator for this object here. If this angle goes to 0 or this energy goes to 0, that propagator goes on shell. So the amplitude for this is just going to blow up. So these are both examples of infrared divergences. So this QCD is a gauge theory, and it's a gauge theory which has infrared divergences at least at this level. So the amplitude will diverge in the infrared. They will only be finite if you properly sum the case where this emission is real plus the case where this emission is virtual. So at the end of the day, there's the Bloch-Nozick or Kinoshita-Nauenberg theorem that guarantees that your final amplitude is finite. So if you sum over everything, all real and all virtual graphs, the answer is finite, but separately the real and the virtual amplitudes are not. And it typically diverges logarithmically in the collinear limit and in the soft limit. And both are examples of infrared divergences. All right? So I can probably now try to answer Jean-Yves' question. If you build something which is just made out of angles, you're going to be in trouble with one or the other. Right. So one of the idea is that if you have an observable which is explicitly sensitive to either of these divergences, you can more or less forget about calculating it in QCD. Because this means that if you try to calculate that observable in QCD, you'll get a logarithmic divergence, essentially a logarithm of the ratio between whatever your scale is and lambda QCD. And so this logarithm is only going to be regulated by whatever non-perturbative phenomenon you're going to have. And in this case, it means that you cannot say something in perturbative QCD without knowing what happens in non-perturbative QCD. So typically, whenever you want to discuss some observable in the final state, it's actually crucial for what we're going to do next. You want an observable which is what we call infrared and collinear safe. And that means, I'm going to come back to thrust at some point. So imagine you have an observable, whatever observable, that's defined based on, so ON is defined, that's the value of your observable for n momenta. At the end of the day, if you want to calculate, I don't know, if you want to calculate the 1 over, say, d sigma dO, the distribution of that observable, you're just going to sum over any possible number of particles. There's going to be the integration over your n-body phase space. They're going to be the matrix element, or the cross-section in this context, for that phase space point. And then you're going to have delta all right, so this would typically be the distribution. So given you integrate, if you forget about this, this is just one, or this is just a total cross-section, and you look how the total cross-section spreads as a function of your observable. So in that context, what you want in order for these observables to have a chance of being computed properly in perturbative QCD is that on the one hand, it should not be sensitive to collinear emission. So if you do a collinear emission, you essentially rely on the fact that after this collinear emission is going to give you essentially a plus infinity in the real emission case, a minus infinity in the virtual emission case, and you want these two to cancel. Otherwise, you're in trouble. All right? That's clear for everyone? And so this means that you want your observable for, say, let me start with the soft case. You want the ON+1 for K1, Kn, K. In the limit where Ek goes to 0, you want this to give the same value as your observable without the emission. So that infrared safety. And now if you take any of these particles, let me take the last one. I'm going to split Kn collinearly. So I'm going to split Kn into lambda Kn 1 minus lambda Kn with lambda between 0 and 1. This gives you the same as if you didn't have anything, as if you didn't have that collinear splitting. So these are the two conditions that, well, if you tell me I have an observable that doesn't satisfy this condition, I'll tell you, go ask someone else. This is, I think, this is crucial in the sense that if you want to be able to calculate these objects in perturbative QCD, this is almost a prerequisite. I can think actually of a few, might actually get there towards the end of the lecture. I can see actually some rare cases where this is not obviously the case, but forget I said that until February. So this is really important. If you don't have these properties, essentially you can forget about calculating things in QCD. There's a very typical example of something which is not infrared safe, is the number of particles in the final state. All right? If you want to count, so imagine you want to count the number of particles in the calculate the number of particles in the final state in QCD. You're going to start. I'm going to have E plus E minus 2 QQ bar. How many particles? 2. E plus E minus 2 QQ bar gluon. That's my first alpha S correction. The real correction is going to have 3 particles. The virtual correction is going to have 2 particles. And this cancellation between real and virtual is screwed. All right? So multiplicity is definitely not an observable which you can calculate in perturbative QCD. You can start putting cutoffs and calculate multiplicity above some well-defined cutoff. That's typically what jets are going to do in the end. But if you don't put a cutoff, multiplicity is dictated by non-perturbative physics. Another example, if you want to make a charge track measurement, using only charged particles versus everything, there is something which is extremely delicate to calculate in QCD as well, because the fact that things are charged or not is not well defined, does not satisfy these properties. So if you build something only out of the angles, chances are that adding a soft particle is going to mess up with this condition. So something which is only built out of angles is most likely will most likely be infrared unsafe. So you can actually check fairly easily that these conditions are satisfied for thrust. Imagine you add just one extra soft particle. If you add one soft particle, it doesn't change the numerator, it doesn't change the denominator, so it doesn't change the value of thrust. And if you split something collinearly, the sum of these two terms in this numerator is just going, so lambda k and 1 minus lambda k is just going to give you k, and same thing up and down. So again, collinear splitting obviously doesn't change this value. So this means that at the end of the day, this definition is infrared and collinear safe. It actually gives you a bit more. This is a very, so even when you try to measure different objects in E plus E minus collisions, thrust is actually something you refer to in more generic context. And the reason is that it gives you an axis. So the value of u that maximizes this quantity, which is known as the thrust axis, really tells you this is my preferred direction along which. So what you're doing really here is projecting your energy along this direction, and so this gives you the energy along which you have the most energy. So typically, if you think about an event like this, your thrust axis is going to be this way, and if you think about something completely uniform, your thrust axis is whatever. So coming back to discussing what I wanted in terms of the topology of the event, if you compute an event like this, you're actually going, if the event is perfectly linear, all the projections are onto the thrust axis. So in this case, you'll get t equals 1. If things are uniform and uniform in a sphere, what you can find is that t is 1/2. So to answer the question I was asking in the beginning, what happens if, well, can you characterize whether the event is like this or like that? What you're going to do is measure as a function of thrust between, say, 0, well, actually it's going to be 1/2, the worst case scenario is 1/2, and 1. You're going to measure 1 over sigma d sigma dt. So you just, experimentally, it's 1 over n dn dt, so you just measure, for each event, you measure thrust and you bin that value of thrust. The question is, it something that's peaked close to 1/2, or is it something that peaks close to 1? If it's peaked close to 1, it means that typically your events are like this. If it's peaked close to 1/2, it means your events are like this. So what do you find experimentally? Where is it peaked? It's a 50-50% chance if you have no clue, but so what do you think QCD gives you? This or that? Not 1/2, no. So 1/2, the distribution 1/2 is virtually 0. Actually, the distribution is very close to 1. So it's peaked around there. There's details close to 1, which so the details close to 1 is actually related to the topic of the second lecture. So again, one of the reasons, there are mostly 3 reasons I want to bring this up. One is that this is something I'll calculate and I'll use in the, well, I'm going to use not exactly thrust, but similar things in the future lecture. So the concept of using a shape is important. 2 is to illustrate the fact that doing E plus E minus collision is actually extremely helpful in terms of understanding QCD. Go back to the 70s. QCD was essentially, well, now everyone is fairly confident that QCD is at least a good theory of strong interactions. It was not the case 4 years ago or 50 years ago. And so in that context, being able to measure this and calculate this in QCD and compare what you see with what you predict from QCD was actually a great way of convincing oneself that, that QCD was or is the correct theory of strong interactions. So I'm going to spend probably a few, before the break, I'm going to actually do a bit of calculations for thrust, all right? So do the most simple thing. And again, the idea is not, I don't care too much about thrust itself. This is just a portal to more relevant stuff for these lectures. But again, the idea is to discuss other things and probably show you consequence of infrared collinear safety on the way, different limits of QCD in the collinear and soft limits that I will use in the lectures after this one. So what I'm going to do is start calculating things in E plus E minus in QCD. So E plus E minus, I'm going to assume a photon. Expressions I'm going to give are for photons. You can find Z's in literature. So it's E plus E minus going to QQ bar. This is something that probably all of you should be able to do with your eyes closed. It's really a typical, well, that's really generally a textbook thing. You don't need any of the last 20 progress in amplitudes from the last 20 years. This is generally textbook Feynman graph calculation. What you get at the end of the day is that this sigma, so this is a function of only one variable. You get E plus E minus, you get QQ bar in your final state. The only dynamical quantity, it's symmetric around the z-axis, so the only dynamical variable is the deflection angle between incoming and outgoing. So you can, the most interesting thing is d sigma d cos theta, and if you do this, what you find is this is an electromagnetic vertex, all right? There's no QCD in this thing except saying that there are quarks. But even if QCD was not there and quark were there, you would still have this. So there's the electric charge of the quark squared times, there's a small trace of QCD, if you may say so. If you sum over all possible final states, you have more than one color possible for this quark. So there's a factor NC that comes in. And then all the rest is just, there's a pi alpha electromagnetic squared over 2s as being the center of mass of the energy of the collision, and then 1 plus cos squared theta, which you can rewrite as, well, some function of the Mendelssohn coordinates, which I don't care of. If you integrate this over cos theta, which you can trivially do, you'll get that sigma is EQ squared, or, well, and sum over all possible quark flavor, you'll get an NC sum over the flavors of the flavor squared times some sigma naught, and sigma naught is for and this is nothing but the cross-section for E plus E minus going to mu plus mu minus, for example. So again, I don't want to spend too much time on this, but this is, again, one place where you can sort of, again, back in the days, learn about what QCD does, because you know that essentially if you measure E plus E minus going to QQ bar divided by E plus E minus going to mu plus mu minus, what you're probing is this factor here, which probes at the same time NC and the charges of the quarks. For example, if you crank up the energy or crank down the energy coming from a high energy, at some point you're going to go below the masses of different quarks, and when you go below the mass of different quarks, this thing is going to decrease as well. So this is, again, this is one very basic observable where say the fact that quarks are in there is observable. So what I want actually to consider instead, where the fun starts, is E plus E minus going to QQ bar and a gluon. And the gluon can be radiated either from the quark and the anti-quark, so there are two graphs to compute for the real emissions, plus one virtual graph where the gluon is a loop anywhere in this process. So I'm going to call this P1, call this P2, K1, K2, and K3. One thing I forgot to say at the beginning, I tend to do research on the Blackboard, which means that with time the size of my writing is probably going to decrease. If at some point you have problems reading, let me know. So, again, you can consider evolved or today amplitude techniques to calculate this. It's actually doable without too much pain using standard Feynman graph calculations. What you get at the end of the day is that the average sum over the squared amplitude is, there's a 4 pi. Again, this is a few pages calculation. I don't know, how painful would that calculation be in I don't know, using modern tools? Yeah, exactly. So there's, well, now interesting stuff comes in. Obviously, this is a QCD vertex, so this you finally start to see alpha S in here. You have CF. Does everyone know what CF is, or do I need to go over that again? So this is just a Casimir factor for QCD for quarks in the fundamental representation. There's an NC squared And then there's the kinematic piece, which is p1.k1 squared plus p2.k1 squared plus p1.k2 squared plus p2.k2 squared divided by s k1.k3 k2.k3. All right, so in terms of kinematics, typically the three particles in the final state, quark, antiquark, gluon, are going to be within the plane. So the number of degrees of freedom you'll have to integrate over all possible orientations of this plane. And then within the plane, there's energy momentum conservation within the plane, which means at the end of the day, you do get only two relevant kinematical degrees of freedom. And what I'm going to use is define xi, which is, I never remember where to put the factor of 2, is 2ei over square root of s. And this is such that x1 plus x2 plus x3 equals 2. That's just momentum energy conservation, right? E1 plus E2 plus E3 is square root of s. All the xi's are between 0 and 1. And more importantly, you can write 1 minus x, so 1 minus x1, let me put it this way, is x2 times x3 over 2 times 1 minus cos theta to 3. Deriving this, I'll let you, I actually let you, I leave this as an exercise. This is literally a two-line calculation. So if you integrate over all possible orientations of this plane, and you'll be left with a cross-section which is just a function of x1 and x2, dx1, dx2, and what you get is 2 over 3s times eq square and c. I'm missing an eq square, I guess, in this expression. Times alpha SCF times alpha electromagnetic squared times x1 squared plus x2 squared divided by 1 minus x1, 1 minus x2. So this is mostly boring or uninteresting, except if you start discussing physics with it. So do you recognize some of the things we've talked about earlier in this expression? What do you expect for the emission of that gluon? Do you expect anything fantastic or specific happening in some limits? Soft and linear. If your gluon becomes soft, it essentially means that x3 goes to 0. If x3 goes to 0, it means both x1 and x2 go to 1, and then this amplitude blows up. Or if you look directly at the cross-section blows up, the differential cross-section blows up. If you look directly at the amplitude, you see that you get 1 over the energy squared in this context. The second limit is, again, if, say, K3, the gluon here becomes collinear with K1, this dot product here blows up as well. So this is the collinear limit. K1.K3 is E1, E3 times 1 minus cos theta 1, 3. So again, the amplitude blows up in both the soft and the collinear limit. And again, if you take the angle between, say, 2 and 3, because that's the one I wrote, between 2 and 3 going to 0, so if you take this cos going to 1, then x1 goes to 1 as well. And so that means that it's visible in this context as well. So what this, in a way, I don't care that much about the exact expressions here. What I'm going to insist on in this context is that they feature the soft and collinear divergences, all right? And based on that, there are actually a few interesting things you can do. There are a few things you can do. Let me drop this for the moment. So the first thing you can do is sticking these expressions and compute thrust. All right? Well, before I jump into that, just a comment on what happens if you want to compute the total cross-section at order alpha s. If you want to compute the total cross-section, you already have it at order alpha s to the 0. That's the sigma, which is nc sum of eq squared sigma 0. If you want to compute it at the first non-trivial order in alpha s, typically you'd integrate this over x1 and x2. And obviously this integration is not finite. This is obviously infinite. All right? So this is really a trace that if you want to calculate the total cross-section, you not only need these real emissions, but you also need the virtual emissions. The virtual emissions are going to have essentially a delta 1 minus x1, delta 1 minus x2 in that form. And at the end of the day, the sum of real and virtual gives you a finite correction. Now, typically, if you use an observable which is not infrared Konya safe, the same thing is going to happen. If you compute it on order alpha s, there's going to be a genuine infinity coming from the fact that your real and vertical contributions do not match, do not connect to each other. So in the case of thrust, if you want to calculate this, if you just have two particles in the final state, this is trivial, right? If you have two particles in the final state, thrust is 1. So at order alpha s, 1 over sigma, at order alpha s to the 0, this sigma dt is just delta 1 minus t. There's no big corrections here. So the next step is to compute thrust for this case here. So I'm going to step away from t is exactly equal to 1. If you take t, which is smaller than 1, the only way to get t smaller than 1 at order alpha s, the virtual correction is always going to be just qq bar, so it has t equals 1. So the only contribution you'll get is from the real emissions. And so you need to be able to compute. So I'm giving you a system with quark, anti-quark, and gluon, and you need to be able to compute the value of thrust. It's not, again, I'll leave it here as an example. T for just a system with QQ bar gluon is just the max of the xi. It's not really complicated to show. The idea is that once you define u for a given u, a given direction splits the event into two hemispheres, one on the positive side, one on the negative side. Because of energy conservation, both hemispheres give you the same value. And then if you only have 3 particles in the final state, you can choose the hemisphere which has only 1, and in that case, this product is x. Yeah, this is literally, again, 2-line calculations. Once you realize you can break things down in a hemisphere and assume there's only 1 in the hemisphere of interest. So if you do that, again, the calculation, you'll integrate this expression over dx1, dx2 with a delta of max of xi equals t. All right? And what you'll find is, and that's an expression I obviously don't remember by heart. I'll use that later. What you get is 1 over sigma, this sigma dt is a complicated expression, alpha cf over 2 pi, that's something you probably could have guessed, times well, again, the expression itself is not really interesting. Well, the details of the expression are not really interesting. That's a 3 t1 minus t times log 2t minus 1 over 1 minus t minus 3 2 minus t 3t minus 2 over 1 minus t. Again, why would I care about this expression in the context of what we've been discussing so far? Is there any specific feature you might be interested or puzzled by? Interested in or puzzled by? Well, first of all, where does this peak? What's the peak of that distribution? Remember, that was the original question, right? Where is thrust located? Is it close to 1/2 or is it close to 1? First of all, because of this, we know that this is bigger than 2/3. the sum of 3 objects has to be 2, the max is at least 2/3. And the max, this 2/3 is realized in the exact configuration, in the Mercedes configuration. So definitely not 1/2, as Ben was saying earlier. Then that's not even reachable at order size. So obviously you see, well, obviously, the 1/t I don't care, obviously, because t is bigger than 2/2. But on the other hand, you see that there is a 1/1 minus t log 1/1 minus t in this context when t goes to 1, and similar is a 1/1 minus t in the second term. So trivially, this is peaked when t goes to 1. Would you expect y? Let me rephrase that question. In going from here to there, where would this 1 minus t dependence come from? Well, look at this expression here. What happens if t goes to 1? If t goes to 1, you start probing xi going to 1 as well. And if you start probing xi going to 1, you start probing the divergences when x goes to 1 in this expression here. So again, the limit where t goes to 1 is really the limit where, again, your event looks like this. So that means either on top of the QQ bar, you have somewhere a soft emission, which doesn't matter, or you have a collinear emission, which again doesn't change the fact that the event is perfectly aligned with a back-to-back set of particles. So again, this, at the end of the day, this is something that we're going to discuss over and over again in the next lectures. Even though, well, you can do the exact calculation. This is not what I'm going to be interested in for most of the cases. Again, if you want something, I'll send you to the go ask David or Ben or Sebastian or probably a few other people. What I'm going to be mostly interested in is the limit where these emissions are soft and collinear, and there's a reason for that that I'll discuss in due time. And in this limit, you see that even though your observable is finite, so if I give you any value of t which is different from 1, this expression is finite. So we do have something which is infrared and collinear safe, so the expression is finite in QCD. On the other hand, there's a reminiscence of these infrared and collinear divergences under the forms of essentially logs. Well, I'm saying logs because imagine integrating this over t. This is going to give you a log square in 1 minus t, and this is going to give you a log in 1 minus t. All right? So that's something I'm going to discuss over and over again. And in particular, how to treat these logarithms in QCD is going to be the most of what I'm going to discuss next Friday. All right? So there's only 2 things which are going to take 1 minute that I'm going to do now, and then we'll cut and discuss jets on the second part. So again, bottom line is that distribution is predicted as predicted by QCD, is peaked around 1, and it's actually what you see experimentally. No big surprise. If it were not, I would probably not be here today. At least not talking about this. There's actually 2 limits I'd like to discuss because they are going to be, again, they're extremely generic things in QCD as well. Take this expression, either this one or that one, and look what happens if you take the collinear or the soft limit. All right. So if I take the collinear limit, you can just replace. So I'm assuming that theta 1,3 is going to 0. So small theta 1,3. In that case, I'm going to say I'm going to rename x3 as a variable z, and I'm going to use a variable. You have 2 options, either t, which is 1 minus cos theta 1,3, or alternatively, you can just use theta, which is theta 1,3. Either one. So the question is, what happens in the limit where t or theta becomes much smaller than all the variables, all the other variables in the problem? And in this context, actually not. What you're going to do is use this expression over here. Well, the one for 1 minus x2 is blah, blah, blah. You can rewrite 1 minus all the x's as a function of these variables. It's just a change of variable. You know you only have 2 degrees of freedom, right? So it's just a matter of making a change of variable from x1, x2 to z theta. And what you get is this sigma is, how do I write this down, is just the Born level cross-section. And by Born, I mean this is E plus E minus going to Q cube R. Times some function alpha CF over 2 pi. You find a 1 plus 1 minus Z squared over Z. And you find, well, dZ, if I want it this way, d theta squared over theta squared. And this is again generic. What you find here is that there's a logarithmic linear divergence. So when the angle goes to 0, you have a logarithmic enhancement of those emissions. And so if you have any, actually I did it for, this is an explicit example for E plus E minus going to Q cube R, but this is actually more generic in the sense that if you have any form of an amplitude where you have a quark here, and you want to study the limit where you emit a collinear gluon of this quark, this collinear gluon can carry a fraction z of the initial quark's momentum. So think about it in this context. You start with 1 and you go into 1 minus z from the quark and z for the gluon. This is going to be the case. This expression is just going to be the expression without that collinear splitting. And this, probably including the alpha s, this is known as the Alterli Parisi splitting function. And again, it's generic. Whenever you have a quark branching into a quark, and branching collinearly into a quark and a gluon, you have a collinear divergence with some function of z which describes the weight and how the splitting happens in z. There are different ways to calculate that. You can actually explicitly forget about this and calculate just this part of the graph and show that it works. The advantage of this is that you can then do it for gluons, and you would also have a collinear splitting function for gluon going to glue and gluon going to Q cube R. The last thing is, so this is the collinear limit. What happens if you take the soft limit? If you take the soft limit, then what I want to look at is this expression here. If you take the limit k3 goes to 0, essentially k1 and k2 become the equivalent of their Born level momentum. And in that case, what you can do is actually, again, factorize out of this expression the Born level amplitude. And what you get is that after integration, this sigma, so I'm taking the limit E3 going to 0, what you find is that this sigma Q cube R gluon is d sigma Q cube R. So again, the Born level cross-section times the function, which is alpha s CF over pi squared, times k1 dot k2 over k1 dot k3, k3 dot k2, times delta and again, this is, again, both these expressions are remarkable results in the sense that they allow you in the limit, either in the collinear limit or in the soft limit, they really allow you to factorize your either amplitude or cross-section, square amplitude or or cross-section, into whatever was happening without that emission times a factor which is just related to the emission itself. So this is the Alterli splitting function. This is usually referred to as the antenna formula. And again, it generalizes in the sense that if you have a generic process, whatever pair of particle I and j you're going to take from this, you're going to have the probability for emitting a soft gluon, which is like ki dot kj over ki dot k, k dot kj, delta k squared d4k. The only thing that's going to change between what we did here in the generic case is that the color factor in front of it, instead of being CF, is going to be a more complicated beast depending on the whole structure of the event. But if some of you have seen some of Einan Gardy's seminar, he's actually coming to speak here something like once a year. So if you've been here for more than a year, you've probably seen him giving a speech on that. This is essentially the very first line of what he does. It's the fact that you can essentially every dipoles, take any pair of current particles, that's a dipole, they can radiate a soft gluon according to that kinematic pattern. For people doing small x physics, this is the same, essentially the same as the BFKL kernel, which has x minus y divided by x minus z, z minus x. You'll have this kind of soft gluon emission patterns in all over the place in QCD. This is a typical case that you'll have. So during the first part, we've been discussing E plus E minus collisions, and in particular E plus E minus going to QQ bar and an extra gluon. And what we've seen is that at the end of the day, the events tends to be organized along along two preferred directions. At least that's what we saw from the first part of the lecture. And the idea is trying to characterize this type of structures where the events are organized in several preferred directions in a slightly more systematic way. And to do this, we are actually going to introduce the concepts of jets. And I'll start with E plus E minus at the moment. I'll carry on with PP collisions later in this lecture. So again, part of the motivation is that initially, as we've used thrust in the first part of this lecture, the idea of using thrust is to show you that most of radiation, so this extra gluon on top of these quark and antiquark, the extra gluon is mostly going to be either somewhere soft and so not really contribute to the flow of energy in the event, or will be collinear to the quark or antiquark produced in the hard process. So one thing is that you probably want and try to identify these directions of energy, and that's essentially what jets are going to do. And so the idea is to extend this concept where you would have two different directions to higher number of hard directions in the jet. In particular, we've seen that even though most of the direction is either soft or collinear, you can sometimes have an event where your topology is going to look something like this. And typically, while in this case you would expect these directions to correspond to the quark and antiquark in your event, this would typically correspond to rare occasions where on top of the quark and antiquark you would have an extra hard gluon, so gluon which is not soft or neither soft nor collinear, which would be radiated, so a hard gluon somewhere at large angles. And so typically this would happen in an order at a rate of order alpha s. And you can even go to higher multiplicities. If you go to higher orders in the perturbation theory, sometimes you will observe events where the situations looks like this, where typically you would have even more hard directions inside your event. And so this would start typically at order alpha s squared. And so again, you'd naively, from a conceptual point of view, you would expect this to be an initial quark and antiquark, hard quark and antiquark, accompanied by sometimes soft and collinear radiation, while in this case you'd expect to have both a hard quark and antiquark and an extra hard gluon on top, each of them accompanied by soft and large angle radiation, and so on and so forth if you go higher in the perturbation theory. So really what you want to do is say that a jet, in this context, you want essentially to be able to say this has two dominant directions, this has three dominant directions, and so on and so forth. And so that's really the idea behind a jet. You would say a jet is literally a direction of dominant energy flow in your event. And that's genuinely the conceptual idea. And behind that conceptual idea, there's another one, which is you would say this is a quark-antiquark process at the core of the event. This would be a quark-antiquark gluon, and so on and so forth. And essentially, this tells you that these jets are, give or take, measuring the initial hard partons in your event. So this is really the idea that everyone has in mind when speaking about jets. you say that a jet is a proxy for one of the hard, highly energetic partons created really at the heart, at the very first stages of this kind of events. So this still needs to be taken with a grain of salt, because an initial hard parton, or even just a parton for that matters, is actually not a well-defined concept in perturbative QCD, or even in QCD. What you mean by a hard parton at Born level, so the smallest order of the perturbation theory, is well-defined, but then once you go to higher orders in the perturbation theory, what you mean by a hard parton, even by a parton, is not really something that makes sense order by order of in the perturbation theory, in the same sense that multiplicity is not a concept, or is not a quantity which is infrared and collinear safe. The parton itself is not a concept which is infrared and collinear safe. So for that reason, one can say that a jet is really you don't want jets to be ill-defined. So you want essentially jets to be a well-defined version of a hard parton. So while this is just a conceptual view, this is genuinely the object that makes sense, and that's well-defined at all orders of the perturbation theory, and so on and so forth. So in that context, again, keeping in mind just this analogy, the fact that conceptually a jet is meant to be a proxy for a hard parton, you can come back and say that an event like this has essentially two directions of energy flow. So it's a two-jet system. And again, conceptually, each of the jet would correspond to a parton. In that case, you'd expect this to essentially be a hard QQ bar system. While in this case, you'd have a three-jet system, which essentially 1, 2, 3 directions of energy flow. And again, this is expected to correspond to a quark, anti-quark, gluon kind of hard event. Again, the attribution of quark, anti-quark, and gluons among the three jets is a different topic. I'll come back to this in the fourth lectures, hopefully. By the way, actually, the observation of events like this, the observation of events where you have three jets, three well-separated jets in the event, is actually a contribution, the way that the gluon was discovered, and it's actually been 40 years ago last June. So really, the observation of this type of events is a key observation that actually played a significant role in the history of QCD. Now again, if you start looking at events like this, the question is how many jets do you expect to see here? And that might depend on, well, that might vary from one people to the next. Someone is going to say, well, there's 1, 2, 3 different kind of directions. Someone might say, well, there's actually this is 2 different directions, all right? So depending on your, I don't know, your feeling, depending on your mood maybe, at some point you will classify this either as a 3-jet event or as a 4-jet event. And this is exactly what I meant by saying that the jet is meant to be well-defined while a hard parton is not a well-defined concept. So the idea of whether this is mimicking 1 or 2 partons is not something which is well-defined. In particular, it means that, say, assume this guy comes from, say, a gluon splitting into 2 gluons. So this gluon would give you something here, this gluon would give you something there. There's a level of arbitrariness in saying either these 2 are collinear enough so that they belong to the same jet, or these 2 are not collinear enough and so they belong to 2 separate jets. So again, the idea is that we define jets in a way that this is fixed and well-defined and calculable in QCD, while regardless of the fact that the underlying concept of parton, is itself not well-defined. So at the end of the day, the idea is that there's a level in this analogy between jets and hard partons, that essentially the arbitrariness, there's all the jet definitions, all the ways that we are going to define jets, essentially have in common that at some point you need to define what you mean by collinear or not collinear. And the idea is you will typically do this by saying a jet has a certain opening radius, usually called R, in which you say everything in between is part of the jet, everything outside is no longer part of the jet. And so that notion, that arbitrariness in defining what is collinear and what is not collinear is partially encoded in this concept. So the strategy in terms of saying these are the jets in my event is always the same. You're going to say, I start with a bunch of initial particles. And out of that bunch of particles, what I want to do is find a method that's going to give me a list of jets. And the way to get from particles to jet is what we call the jet definition. This is, give or take, made of two ingredients. The first one is an algorithm. The algorithm is generally the recipe that you can write on paper that allows you to, or implement in a computer, that goes from particle to jets. And then the extra thing you need to specify is that recipe can have 3 parameters. And so to define jets uniquely, you also need to specify these parameters. Typically, these parameters are going to tell you to what degree, well, what collinear means, essentially. To what extent two things are collinear, and when do you stop calling them collinear. So what I'm going to do in the rest of this lecture is essentially going to give you an overview of what are the most common jet definitions used in E plus E minus collisions, and today at the LHC in PP collisions. So they usually split into 2 main categories. And so the first category I'd like to discuss, let me try and see how I organize this. So the first category I'd like to discuss is cone algorithms. And I'm just going to limit myself to the case which is the Sturman-Weinberg cone. It's somewhere in the late 70s. I never remember if it's 77 or 79. But so again, keep in mind the idea which is here. Okay? So to do this, what you will do is define an event is n jets. Again, the idea here being to say if I have an event, I want to count how many of these jets do I have. If the energy let me do it this way. If the energy, so the energy is square root of S in the event, is in n cones of opening angle to R, and not in n minus 1. So again, the idea in this context is that you, for this kind of event, you're able, provided R or 2R is large enough, so provided you have an opening here which is 2R, you would say, in this context, I'm getting the energy into 2 directions, so that would be 2 jets. In this case, I need 3 of these cones, or circle on a sphere if you prefer, in this E plus E minus topology. In this case, I have 2. In this case, I would have 3. And depending on the value of R, I would have either 3 or 4 in the rightmost event. All right? So the question is this infrared and collinear safe? Because at the end of the day, I told you I want to make something which is well-defined, and one of the things I mean when I say well-defined is something which you can actually trust in perturbation theory, which means that needs to be infrared and collinear safe. So if you add a collinear emission, so if you split one of these guys into two collinear particles, obviously the two collinear particles are going to remain inside that one circle or that one cone of opening angle 2r. So this is a concept, this is a definition which is infrared safe, which is collinear safe. Now if you add a soft emission, then the situation becomes a bit more complicated. Imagine you add a soft emission here. If I want to capture the full energy in the event, obviously I'll need to add an extra jet here. And so adding a soft emission changes how I classify or how I decide the number of jets in my event. And so this means the definition is not infrared safe. And so this is why actually what you're going to say is all but a fraction epsilon of the energy in the event is within cones. So that means that if you add a soft particle, which carries essentially no energy, you're still allowed to lose some fraction epsilon of the energy. So once this emission becomes soft, that does not need to, that does not require an additional jet, and so the number of jets in the event is going to stay the same. So this checks at least the basic requirements that the definition is infrared and collinear safe. Just as a side note, I told you earlier that whenever you have ratios of scales and ratios of angles, of angular scales or energy scales, you should expect logarithms coming from the structure of QCD. This is an example where technically this is finite, so real and virtual corrections conspire to give you a finite answer at every order of the perturbation theory, but at a given order of the perturbation theory, you should expect to see some logs of r and some logs of epsilon coming from soft, in this case, and collinear emissions in that case. So even though at the end of the day it's finite, you will have alpha s accompanied by logs. And again, that's something we're going to discuss over and over again in the course of these the next lectures, in particular in the next one. So how nice is this? Well, if you want to compute the rate, you can try to compute this in QCD, right? You go back to what we did in the first hour, where we derived the essentially differential cross-section to have for E plus E minus going to QQ bar gluon. And what you have there is, well, you can say, for example, calculate F3, which is the rate of events which are classified as 3 jets. And if you want a jet which is which has 3 jets, that means you require all 3 quark, antiquark, and gluon to be in different cones and to be in different and to carry at least a fraction epsilon of the event, because if one doesn't carry a fraction epsilon of the event, it can be safely discarded and you're back in the 2-jet situation. So for this, you're essentially going to impose that all the xi's are bigger than epsilon, and that 1 minus cos theta, any cos theta ij has to be bigger, smaller than 1 minus cos, probably 2r here. So essentially what you will do is just integrate this over x1 and x2 with this constraint, remembering that you have actually constraints between the different x's and the angles. So I'll give you an example of this later, so I won't give you this, this calculation now. That said, you can be happy with this, and then someone else is going to try and make a more precise calculation. Say, now I'm going to try and go to alpha s squared, alpha s cubed, and so on and so forth. And if you do this at some point, you're going to, well, things are going to start becoming difficult. One of the reasons is that you're trying to pave the sphere, so all the angles in your event, you're trying to pave the sphere with a bunch of cones on circles in that sphere of opening angle 2r. And paving the sphere with circles is not always nice. So that means that all these constraints, which look easy if you only have 3 particles in the event, once you start adding more and more particles in the event, getting actually the list of these jets is complicated. It's going to be complicated for 1 in the case where you want to do perturbative calculation, and for 2, imagine you want to do this reconstruction in an experimental or practical context where you have a full event simulation or a full event inside the detector. The number of particles is quite large, and so practically speaking, finding these cones is delicate. So even though this is something which is infrared and collinear safe, practically speaking, this definition is actually quite impractical. So these actually led people to try and look at something different. And so this is going to lead me to the second big category of jet definitions. And this is something, so the idea behind this is to say, look, we essentially have an idea of what we know, we sort of know what, or have a picture of how these jets are built. These jets are built from radiation which is going to be collinear to an incoming hard guy. So you'd expect this to be dominated by radiations which are going to be soft and collinear compared to the original hard parton. That's the dominant physics mechanism which is at play in implementing that concept that the jet is an initial hard parton. So instead of saying I'm going to define that jet just as a flow of energy in the direction of the initial guy, I'm going to go and define it backwards. So I'm going to say, if I have a list of particles like this, I would expect them to come from successive branchings of partons. And so instead of reconstructing a jet as a whole object, I can try to undo this list of branchings. And so this is what we call an iterative or successive. I'm going to focus on pairwise. You can do more fancy, but this is what I'm going to focus on, recombinations. And besides code algorithms, this is the second big category. Again, the two implement top-down and bottom-up approaches, if you wish. So to do this, what I'm going to do is define a distance. Let me call dij and leave that hanging at the moment. I'll come back to this later. So you define a distance between any pair of particles in your event. Okay? And what you're going to do is say, first, find minimum of all these dijs. 2, well, I can just say, well, these minimum dijs, they probably come from a common ancestor, so I'm going to recombine them. Recombine, say, ki plus kj into ki plus j. So from n objects, you go to n minus 1, and you iterate. Like with any iterative process, you need to tell when to stop. And so on top of that, I'll have to give you a stopping condition. OK? All right, so far so good. So we're left with 2 questions. Probably one more interesting than the other, which is what kind of distance do you want to take for this? And if there are amplitude people in the audience, they should probably be able to make an educated guess on this. In particular, I told you my goal is to try and undo this branching that would naturally occur in a type of QCD cascade. Now, the question is, when do you expect a branching to be most probable? And for that most probable branching, you'd expect the distance. You'd want to have a small distance for something that happens with most probability so that you can undo what happened most probably. And typically what's going to happen, and we saw that already in the first hour, that if you have a branching like this, when the branching becomes soft and or collinear, what happens physically, well, technically speaking, when you're trying to write the amplitudes for these guys, is that there's a propagator which is becoming close to on-shell, and that's what creating a high probability for this branching to happen. So the natural way of actually defining a distance is actually to use the Mandelson invariant of these two of any pair, which is, if you wish, that would be ki plus kj squared, which I can also write as the invariant mass of the ij pair. So in terms of QCD, this is what you'd naively expect, and so this is the dij that I'm going to use first, and this is what people call the Jade algorithm. Let me check if I forget anything here. No, this seems about okay. All right, so what you need on top of this is, I told you, I've defined my distance. Now I need to tell exactly when to stop. And so what I'm going to do is just to say stop when the mass I'm getting is bigger than some cut. So when the mass you get, the invariant mass you get between two different objects is bigger than some fraction of the total energy of your event, you're going to stop. And so at the end of the day, y-cut is a free parameter. Essentially, y-cut controls what you mean by collinear, soft, and all this. So y-cut is the parameter that implements your degree of arbitrariness in defining jets. So does this work? Well, is this infrared and collinear safe first? Well, if you take an emission, a soft emission will essentially correspond to one of the k's which is going, one of the energies of the k's which is going to be very small. And so this means that this for the sum ki plus kj is going to be essentially ki squared, which tends to 0. So as we see, it's essentially what we saw in the first hour, right? When one of the particles becomes soft, the propagator goes on shell, and so its Sij goes to 0. So this means that if the distance goes to 0, it is going to be the minimum and being recombined. Similarly speaking, if you have a collinear emission, the collinear emission has the same property than Ki and Kj become collinear. Their sum is going to 0 as well. And again, if you have a collinear emission, the Dij is going to go to 0, and that's something which is going to be recombined early on in this iterative clustering process. So at the end of the day, this provides both an infrared and collinear safe definition. So first, the first box is checked. You can also try and compute this in perturbation theory. And so we can just go back to what we had here and try to see what happens. Can we compute the rate, the fraction of events that will have 3 jets? And so if you do that, you need to be able to compute the invariant mass Mij squared. And Mij squared is 2 times Ei times Ej times 1 minus cos theta ij. That's simple for vector manipulation. So if you use this definition of the x's and this definition, this relation between the cos and the x's, what you find at the end of the day is that this is, well, first s over 2 xi xj times 1 minus cos theta ij. And so this is s times 1 minus xk, and in this case with 3 particles, when k is always, well, use k to denote the index, which is different from both I and j. So if you take as m12, that would be x3, and so on and so forth. All right, so if you want to have 3 jets in your event, it means that all of the s times 1 minus xk need to satisfy this, needs to be above your cut, your stopping condition. So that means that you'll have 3 jets if 1 minus xk is larger than y cut for all k. And again, this is something which you can calculate. At the end of the day, you'll get that your 3-jet rate is the integration dx1 dx2 times whatever we had there, 1 over sigma, normalizing this to get a rate and not a cross section, dx1 dx2 times the product over I theta 1 minus xi bigger than y cat. This is the integration that everyone should be able to do. I have the answer somewhere if I can find it. No, not here. There we go. So what you find at the end is something which looks like alpha s cf over pi. So it's proportional to alpha s. That's good. Times 3 1 minus 2y log y is y cut in this context. Just log y over 1 minus 2y plus 2 log square y over 1 minus y plus 4 li2 of y over 1 minus y minus pi cube over 3 plus some rational function 5 minus 12y, so 2 minus 9y squared over 2, which is per se mostly useless. Well, no, let me take that out immediately. There's two interesting things about this. One is that you get a Qcd prediction. Ideally, you'd want something higher, alpha squared, and so on and so forth, but at least you get a Qcd prediction, and you can get to compare whatever this prediction is doing, whatever this is predicting, to any observable, something you would measure. And this kind of measurement is actually what you need, or you needed something like 40 or 50, well, 40 years ago in order to try and convince yourself that Qcd was the right theory of strong interactions. If you can measure this thing compared to whatever your analytic predictions are, if you find something which is in agreement, good. You build trust in Qcd. The one thing I'd like to attract your attention to is, again, the fact that this is finite, so this is infrared, this is obviously infrared and collinear safe, and the reason is obviously visible from here. We've seen that divergences were coming from the region where x1 or x2 was going to 1. These are the two divergences in that expression up there. And what y cut does is obviously shielding this divergence. So you effectively, that's obvious from this, you obviously try to prevent the y cut, prevent yourself from getting close to x1 and x2 equals 1, and the leftover is not surprising. You do expect to have logs of y cut when y cut becomes small. When y cut becomes small, you're allowed to go close to x1, x2 becoming 1, and so you'd expect to feel logarithmic traces of soft and Courier divergences, and this is exactly what you have. You have one example here where there's a log square which would typically correspond to soft and collinear to emissions, which are both soft and collinear, while you have a log here. Actually, this log, you can show that this is hard collinear emissions. So this is a single log which is collinear but not soft. And on top of that, you get finite alpha S corrections, which are what they are, tough luck. Okay. Yeah, so if you want, one thing you can do is you can try and look at the phase space in x1 and x2. So anyway, they're essentially bounded to be in this triangle here. So x1, xi smaller than between 0 and 1, and x3, which is 2 minus x1 minus x2, also between 0 and 1. What essentially you're doing is, you know you have some danger in that area. What you're really doing is limited your region of integration to something which is y cut away from 1. So you're really integrating in a region where you know things are finite. So you're usually happy. You'll need to probably treat these logs at some point, and again, I'll come back to that at some point as well, maybe, well, probably next week. One thing you may want to do once you have this is the same argument that we discussed with the code. You want to go to higher orders in the perturbation theory. And so you want to start computing alpha squared, alpha cube, try to resum those logs, do all sorts of fancy stuff to build a solid QCD prediction that you can compare to the data and not only be happy that you trust in QCD, but also, for example, extract the value of alpha s. So if you do this, at some point you'll hit an issue. And the issue is the following. Imagine you have an event where you have two hard quark and anti-quark in, and then you have a soft gluon somewhere on this side and a soft gluon somewhere on the other side. Naively, everyone's going to agree with me this should be a two-jet event, right? You have something which appears on the left side, something which happens on the right side. This is obviously two directions of flows of energy. Now, sometimes what can happen is that this event, the first step of this event, is going to recombine the two soft gluons, and that the recombination of the two soft gluons is happening to be somewhere in the middle, somewhere at large angles. And if this was below the y-cut threshold, this can, after recombination, be above the y-cut threshold. So this would actually be classified as a three-jet event and not as a two-jet event. In practice, doesn't really matter because you can always try to make a fixed order calculation of everything. At least for a fixed order calculation, you have to plug in the exact matrix element and do the calculation anyway. But if you start to look into the region where y-cut is small and you want to resum those logarithms to all orders, you'll start having the problem that these kind of configurations are making the calculation much more complicated than you'd hope. So the reason why this happens, before that, so essentially what you want to do is find a different algorithm where this situation, this pathology is absent. And so to do this, what people have considered is just changing the distance. So you still keep the same methodology here, but the idea is to try and find another distance and another stopping condition, or at least a combination of these two, where these potential strange issues are absent. Now, you can just go back to the distance, right? The distance that I showed there, which is 2 EI EJ 1 minus cos. You understand where the issue is coming from. The fact is that when you have a pair, imagine this guy is soft, the distance between this guy and this guy as a soft factor, say this is I and this is J, there's a soft EI times a hard EJ, while if you take the distance between this and that, this has both a soft EI and a soft EJ on the opposite side. And so the fact that you try to take the distance between two soft objects gets an extra small factor compared to something distance between a soft and a hard object. And so this is really what's at the heart of this say problem or pathology. So the way to overcome this is actually not so complicated. That's what people call the Durham or KT algorithm. And for this, you will define dij as being, so you still want a factor which is 2 times 1 minus cos theta ij. And what you're going to say is, instead of taking this, let me take the minimum of EI squared and EJ squared. And the stopping condition still uses the same y-cut approach. So, is this infrared and collinear safe? Well, if for the collinear part, again, if an angle becomes small, this factor goes to 0, and so you expect the distance goes to 0 in the limit where the distance goes to 0 in the limit where the angle goes to 0. So this for the Durham and for the Jade algorithm is exactly the same. Conversely, if you have a soft emission, so if one of the energies goes to 0, again, the minimum here is going to go to 0 as well. So this means that both soft and collinear emissions are going to have their distance going to 0, and so are going to be recombined early on in the clustering and your algorithm is perfectly infrared and collinear safe. So again, this checks all the boxes. You can play exactly the same game as I did here and try to impose that at the end of the day you do get, you can try to compute the 3-jet rate. I will not do it here, but at the end of the day what you'll find is an expression similar to this one, again with double logs of y cut coming from soft and collinear emissions, and finite plus extra finite pieces in alpha S. So this definition is actually well defined, and you see that the use of the minimum here means that if you try to compute the distance between a soft and a hard object, or between two soft objects, at the end of the day the overall, say, softness is going to be the same. So in this context, this is going to be recombined first here, and well, one side first, and so you will, for this kind of events, you will indeed get 2 jets because you've adapted the prefactor. So what you want to do now, what I want to do now is just list one extra algorithm here and then move to PP collisions. There's one other thing which I will actually have to use extensively for the rest, well, for the last series of lectures, so probably 3 to 5. It's something called the Cambridge-Aachen algorithm. Introduced first by, usually when there's 2 names, that means that 2 people introduced it first. So introduced initially by people both in Cambridge and in Aachen. So the idea here is to say that the dij is 2 times 1 minus cos theta ij. And if you haven't fallen asleep for the last half an hour, you should be mad at me for writing down something like this. And the main reason is because this is obviously collinear safe. If you take 2 particles which are collinear, the distance goes to 0. But now if you add an extra soft particle, the distance no longer goes to 0. So there's absolutely no guarantee that an algorithm like this is infrared safe. So remember, I told you I want the distance to go to 0 in 2 limits, soft and collinear. Collinear indeed goes to 0, soft it doesn't. So this is where I can play my joker and say, remember, I actually had 2 degrees of freedom. The distance and the stopping condition. And so I can just make it safe by saying I'm going to stop. Instead of using this distance as a stopping condition, I'm actually going to use the Qcd distance as a stopping condition. And so this means that the minute you start getting, so soft radiation is indeed going to be pulled inside jets, but the minute you'll get something different, well, essentially soft emissions are still going to be put inside jets, properly as they should, because soft emissions will violate this. Well, soft emissions will have a distance below the y cut, and so you will carry on clustering until all the soft emissions have been properly reabsorbed. So indeed, this algorithm is infrared and collinear safe. Collinear safe, obviously, from here. Infrared safe because of this slightly twisted stopping condition. And again, the logic is the same. You try to calculate this in QCD. You can use exactly the same technique as here to find the alpha S expression. You can then try to, there will be the same kind of logarithms in y. You can try to get logarithms in y resum. You can try to make an alpha S to the n expansion. And at the end of the day, in both cases, what you want to do is compute the jet rate, F2, for the probability, the rate for the fraction of 2 jet events, the fraction of 3 jet events, F4, F5, and so on, as a function of y cut. And the goal is to compare whatever your QCD calculation gives you with whatever is measured in the experiment. Initially to gain confidence in QCD, and then to try and measure alpha S, for example. That's the other case. One typical case is F3, which is obviously the probing, for example, the CF structure. If you go to the 4th jet event, you start becoming sensitive to cases where you will have, say, something where E plus E minus goes to quark antiquark gluon, and then your gluon splits into two gluons. So this triple gluon vertex starts popping in when you go to four jet events, and so this is again something that can be, the Young-Mills nature of the non-abelian nature of QCD can be probed by measuring four jet events. All right, so where am I? So again, all these algorithms are perfectly well defined, and actually LEP has used all of them. Actually, mostly Katie and Jade. So for the last bit of this lecture, I'd like to extend this to the case of algorithms in PP collisions. And as I told you in the beginning, the main difference between E plus E minus and PP collisions is give or take the choice of the variables. You want to use energies or momenta transverse to the beam and rapidity and azimuthal angle, so using a cylindrical system of coordinates instead of a spherical system of coordinates, mostly because as you're colliding partons, the center of mass of the collision has a longitudinal boost along the axis of the collision. So what I'm going to do is just going to show you how these objects are these algorithms are generalized to PP collisions, and discuss what the status at the LHC is at the moment. All right, so the first thing is this distance. Let me try to see if I can. Yeah, let me move here. That's probably going to be cleaner. Move this up there. Move this down. And start something cleaner. So now we're doing jets in PP collisions. Again, the idea is define the directions of high energy in your event. One side note, the overall, the motivation for doing jets is slightly different, I think, in E plus E minus and PP collisions. In E plus E minus collisions, as I've tried to say repeatedly, what you want to do is get some constraints on QCD, do some QCD measurements, do some constraints on QCD, while in PP collisions, essentially what you want to do is more the conceptual approach of saying my jets are actually proxies for my hard parton. So the jets genuinely give you an access to whatever hard process was happening at the core of the collision. And so I don't know. If you have a 6 jet event, that could be either 6 QCD jets or hadronically decaying tops, you'd expect this to end up into 6 jet because the top decays into WB and the W decays into QQ bar. So really counting the number of jets is giving you how many hard partons you have, and so you have a list of topologies, a list of hard processes that would contribute to that given number of jets. So this distance can be trivially generalized, right? So I told you, instead of using energies, I'm going to use KT. So I'm still going to use the minimum of KTI squared KTJ squared. And then instead of using angles, I'm going to use distances along my cylinder. And so this is delta R ij squared, which, for a reminder, this is delta, the difference in rapidity squared plus the distance in azimuth angle squared. So this is genuinely what you would, a trivial consequence of the simple change of variable between one and the other. There's still some, so this is how you change the distance. Now there's a subtlety, and that subtlety is coming actually from the change, from the stopping condition. Remember, when you were doing E plus E minus collisions, you essentially have just the final state hadronic activity, and that tells you you're essentially, what this does is take the whole event and break it up in a certain number of patches, each patch corresponding to a jet. Now in PP, that's not quite what you want to do, because the whole event is containing a lot of extra activity coming from pileup, underlying event, initial stage radiation, all these things that produce soft junk all over the place. And you probably want jets to be more localized than this. So what you want to do is say a jet is probably, I want a jet to be somewhere localized in a region of opening or of radius r. And one way to do this is actually to change the way we do the stopping condition and the way we do this iterative process. So what you're going to do is define not only a dij, which is a distance between I and j, but you're also going to define a single particle distance, dib. The b here stands for beam for historical reasons I don't want to enter in. And what you're going to say, in the iterative process, you're going to say find the min of dij and dib. If the min is dij, you just recombine ki and kj into ki plus j, as we were doing before. But if the min is dib, then what you're going to do is say call I a jet. And so as you go along, at some point, all dibs, as dibs become minimum distances, every objects are going to be called jets. So in this case, it's probably better to discuss this on the KT example. So this is the KT algorithm for PPs, what people often refer to as a longitudinally invariant KT algorithm, as compared to some spherically symmetric version. You're going to define this as being kti squared times some parameter r squared. And so just to have an idea of what this is doing, as long as the distances between different particles are smaller than r, wherever you have a kti here, you'll have a kti squared. You'll have, if the angles here are smaller than r squared, this distance is going to be smaller than this one. But the moment the distance between the particles are bigger than the jet radius, actually this is going to become smaller than this, meaning that r squared is generally doing the job of trying to limit the reach of your jet to something of order r. Okay, so this is generally the way the way this algorithm work, and that's the KT algorithm as used at the LHC today. Now, actually, you can slightly generalize this in a way that would allow me to cover all the cases of interest. I'm going to discuss what people call the generalized KT. And this works by saying, now I'm going to take this to some power 2p instead of 1. And there's essentially 3 interesting cases. If you take p equals 1, that gives you the KT algorithm. That's what we just saw. If you take p equals 0, well, this factor drops out, this factor drops out, and now you end up with something like the Cambridge algorithm. So this is giving you the Cambridge-Aachen algorithm. Just a side note, there was a stopping condition here. Now, essentially, this DIB plays the role of a stopping condition. Obviously, if you drop this factor and that factor, whenever the distances between any pair of particles becomes larger than r, you essentially going to start and call objects jets. So this is obviously the r square is indeed playing the role of limiting your extent to a distance r. The third case of interest is actually taking p to be -1, and that's what people call the anti-KT algorithm. And again, you should shout at me because that actually does quite the opposite, exactly the opposite of what I said in the first place. I told you that distance has two purposes, as the purposes of mimicking the QCD branching, and this means in particular getting to 0 in the limit of soft and in the limit of collinear branchings. And now what I'm doing is essentially saying, well, this distance is actually going to blow up if one of these guys becomes soft. So the soft particle is actually going to blow up my distance. So this is sort of counterintuitive. Actually, the logic behind this is to say, imagine I have a hard particle somewhere in my event. If I have a hard particle somewhere, it means that its KTI to the -2 is going to be small. And so this means that if there's any particle in the vicinity of that particle, the distance between that soft particle and the hard particle here is going to be very small, and so these particles are going to be recombined. So as the clustering goes along, particles in the vicinity are progressively going to be recombined with the hard particle here in the middle until you reach a distance r around that particle, in which case the DIB becomes the minimum. And so the net effect is that if you have a hard particle somewhere in the event, if you have a hard seed somewhere in the event, this will actually build up a jet which is actually a perfect circle of radius r, and this is actually not the case of the other two guys. So there are several ways to say this. One is to say that these algorithms are actually very resilient when it comes to adding soft radiation, and this is definitely something that you want in a PP context, because I told you a PP context, you add lots of soft particles on top of the hard event, and so having something which doesn't depend too much on this soft radiation means easier calibration, means smaller sensitivity to probably underlying events, soft things, both in QCD, perturbative and not perturbative. So this is definitely a property that, this is probably the property that made people choose the anti-KT algorithm as their default choice for the LHC. So the LHC now, for 90% or maybe more percent of the cases, uses the anti-KT to reconstruct the algorithm to reconstruct their jets. And this is the main reason. It actually gives you robust jets that are easier to calibrate, and hard jets are genuine circles. In a way, it is a cone algorithm in the sense that you do have you use circles as building blocks. It's a cone algorithm rephrased in a successive recombination language, so without the drawbacks of the cone. There's a whole series of discussions about using cones in these kinds of PP colliders. The Tevatron, for example, used cones. Actually, you can show that all the cones defined at the Tevatron and candidates for use at the LHC 10 years ago are actually either infrared or collinear unsafe. There's one version which is called Syscone, which I worked on more than 10 years ago, which actually is to date the only infrared and collinear safe cone known, one of the only. There are variants around the Syscone idea, but that's the only cone that's infrared and collinear safe in a PP context. I can discuss that over the next weeks if there's an interest. Actually, in terms of practicality, these are actually implementable in a way which is faster than the cone, and so this is one of the reasons why, and so it's more QCD friendly. So this is the reason why these objects are preferred. So the last word I want to have is about the choice of radius. I'll discuss that later in the future, but essentially saying I define my jets using KT Cambridge or anti-KT is not sufficient. If I tell you, again, it goes back to what I was saying at the very beginning, there's an arbitrariness in what you mean by collinear, and so that arbitrariness is lifted by a given choice of R. You fix R, you fix what you mean by collinear. And so unless you specify what R value you've used, or what Y-cut value you've used in the case of E plus A minus, you don't have a uniquely defined, a well-defined definition of jets. So the values of R DLHC for most of the cases use somewhere between 0.4 and 0.7. Typically 0.4 and 0.5 are the defaults for Atlas and CMS. 0.6, 0.7, some alternative. Rare cases, actually more specific cases, which is actually what I'm going to cover when we'll come to substructure, use larger radii. Heavy ion kind of collisions use smaller radii, but that's the ballpark of the values you want to hear. So bottom line, jets are proxies for hard partons. That's the conceptual idea. Practically speaking, you rely on the jet definition to reconstruct your jets, and this is the set of jet definitions that I will use in the next series of lectures, In particular, the default algorithm at the LHC is the anti-KT algorithm, which has this nice property of making round and circular jets. So this is where I'm going to stop for this week. Maybe, yeah, if there's any topic here that you want to see discussed, implementation, algorithmical complexity, sensitivity to soft radiation, discussions in QCD, just let me know. I'll do my best to cover them. Otherwise, next week we're going to move to try and handle and give an idea of how all order QCD calculations works in the limit where you have large logarithms. So thanks, and see you next week.